Okay, well, good evening to all of you, this huge class that's gathered here tonight. Thank you for trekking all the way to Waterloo. And welcome to session 2 of our little module on templates. You were all here last week, weren't you? Were you here last week? You were, yeah. Excellent. In that case, we're going to be able to go really quickly. Because I was kind of hoping we might have a bit of a bigger group than we did last week. But alas. About the first 10 or so slides today, you're just going to go, yes, I know, we saw them all last week. But as I say, I thought we might have some more people and it'd be better to do a bit of revision. But it does mean that we'll get on to the interesting, sort of slightly fun meta-programming stuff towards the end. I wasn't sure we'd have time for. Yes, apologies to anybody who's watching this online. I know the audio isn't as good as it normally is. We're having to use the room microphone rather than the direct connection, so apologies if you can't hear me. I will try and stand a bit closer to the laptop so that it can pick me up properly. Also, Tom is not here to do his usual introduction, telling you all about who we are and what we do, but you guys have seen that all a million times anyway. But I will, for anybody who's watching this, we are still really looking for a place to call home. We've very, very kindly, Cloudflare have lent us their space for the evening, which we really, really appreciate. It's really impressive space as well. So thank you very, very much to them. And if there's anybody else who knows of any meetup space that we could use, that would be awesome. Please get in touch with me or with Tom or with Ollie or any of us via the website. As usual, we encourage you all to come and join our Slack channel so you can talk to us about all the meetup spaces you know about. Oh yeah, and on that, by the way, I should also say thank you to Michael for organising all of this. We really, really do appreciate it. Without you, we wouldn't be going ahead tonight, so thank you. But yes, if you haven't already, and I know you guys all have, but yes, please do join our Slack channel. Just head to that URL, put your email address in, and it will send you an invitation to come and join the CPP Lang Slack. So please do that. Okay, so let's move on with the actual lesson, shall we? Last week, we had our first session on templates. We looked at some template basics. We looked at what are templates, why do we want them, why they're a good thing, why we like them. We looked briefly at how we actually use them. And we'll be doing a little bit more on that tonight about template argument deduction. We looked at the syntax that's used to define templates. So you use the template keyword and then in angle brackets, you put your template parameters. We looked very briefly at writing class template member functions. Normally, or frequently, you write these inside the class, but it's also possible to declare them in the class and define them outside of the class, and the syntax for that is a little strange, a little quirky, so showed a quick example of doing that. And then we started looking at template specialisations, and we'll be going on and doing a bit more about that tonight. And on that subject, we have, you don't get bullet by bullet, but never mind. Animation fail. Never mind. So this week we're going to start with a bit of revision. As I said, I was rather hoping we might have a little, a slightly bigger group than we did. A few more people who didn't make it last week. So I was going to go and have a bit of revision from last week. We're going to look again at explicit specialisations and then go on to talk about partial specialisations, which we didn't talk about last week. We're going to look at explicit instantiation, how you say to the compiler, I want you to generate this template specialisation here and now for me, please, and why you want to do that. We're going to look at something called extern template, which is new in C++11. Theoretically reduced compile times, which is one of the downsides of using templates. And we're going to look at how template argument deduction for functions works. And then I said time permitting because I thought if we had, we might spend a bit longer on the revision. But since you guys are all know everything already, then I won't have to do that. So we probably will get on to the intro to metaprogramming, which will be kind of, I think that might be kind of fun. Sorry?
Like a dense topic.
A dense topic. Yes, we're doing the very, very basics.
It says intro, doesn't it?
Yeah.
You might want to talk about this overload thing with stood visit.
The overload thing with stood visit.
You know this, the overload for, what's it called, lambda functions.
That's, we need to talk about variadic templates before we talk about that, and we'll probably talk about variadic templates next week. And parameter packs and things like that. Maybe even fold expressions, although it's not strictly speaking to do with templates, but that's where they turn up. Yes, so I'll rattle through these next few slides, mostly because they're there and I have to go through them anyway, but you've seen all these before. So why do we want templates? We want templates because they allow us to write code that's generic, that's type safe, that's really, really highly efficient. And as I mentioned several times last week, templates like a blueprint that tells the compiler how to produce a definition. So if we have a function template, that's a blueprint for a function. It's not a function itself, it's a blueprint for a function. If we have a class template, that's a blueprint for a class. One thing that trips some people up if they're coming from other languages, Java in particular, is that C++ templates are purely a compile time mechanism. There's absolutely no runtime leftovers with templates. It's purely a compile time mechanism. And as I say, it's quite different from how generics work in some other languages, in particular in Java. In terms of terminology, it's important to understand, and I mentioned this last week, I mentioned all of this last week, but it's important to understand the difference between a class and a class template, and the difference between a function and a function template. One is an actual, class is an actual new type that you can use. You can declare a variable of class type and use as an argument to a function. A template is just, a class template is just a blueprint for how to build a class. And until we specialize that template, until we instantiate that template with particular arguments, we can't declare a variable of class template type. That makes no sense. So more terminology, we instantiate a template with particular template arguments. So templates take, like functions take parameters, templates take template parameters. And we provide our function with arguments when we call the function. We provide our template with template arguments. And when we instantiate a class template, that produces what's called a specialisation of that class template, and that specialisation is itself a class. That's a real class. You can declare a variable of those types. So templates, as I mentioned, templates are blueprints. They just tell the compiler how it should go ahead and generate the class. And in order to build something, you need to have the blueprints available. So that means, in general, that all of our template code needs to go in header files. That's why you get these boost libraries that are really template heavy, that are entirely written as header files, header-only libraries, and you can have tens of thousands of lines of code in your headers. So that's one of the downsides with using templates. Although they can generate sort of spectacularly efficient code, the downside is that every time you recompile, the compiler has to go and parse all these header files over and over again every time you hit recompile. Tens of thousands of lines. It's got to go through and generate all those specializations over and over again, and it can lead to really lengthy compile times. So there's no such thing as a free lunch. Templates are great in many ways, really fast, really specialized code, but your compile times suffer. Fast runtime, slow compile times, which I think is a worthwhile trade-off, but it's something that drives some people mad about C++, so not everybody agrees with that.
Is there a way you can structure your code?
Yeah.
The headers are file, and then use the compiled version.
Is there a way to structure your code?
Yeah, so I mean, I guess if one header needs, if the header needs all the templates to run, sort of like file that you can just put in.
As we will see shortly, actually, there is a way of saying to the compiler, okay, this particular specialisation of a template, I'm going to instantiate that elsewhere, you don't need to bother doing it now. The other thing you're talking about, there was actually an attempt to do that back in the C++ 98 era. I've got tons of time tonight, I may as well tell you the story. So the C++ 98, when they were coming up to standardise it, this thing about templates was, generating, slow compile times and everything. You think how slow computers were comparatively then. This was a known problem, and they came up with a solution which was a keyword called export. And the idea was you said export template, and then some magic would happen, and it would do basically what you wanted, what you have just suggested. So you'd have like a repository of sort of half-compiled template code somewhere. And people sat around and they designed this facility and they put it in the standard, and then they realized that this was almost impossible to implement for compiler implementers. There was one company called EDG, the Edison Design Group, who actually write the front end for the Intel compiler, I think still to this day. But they managed, or in fact one of their employees, managed to implement this according to the specification. So the other compilers, the big ones they use today, so GCC, Clang didn't exist in those days, but Microsoft, they were never fully compliant with C++ 98 because they didn't implement this export thing. Only EDG did. And so export was widely regarded as a mistake, a really cautionary tale of standardizing something without having had any evidence that not only that it works, but that it's even implementable. So when they came to C++ 11, people wanted to remove this export functionality because basically it didn't work, or it only worked on one compiler, and that was heroic efforts. But they were very reluctant because they knew that EDG had spent a lot of time implementing this. But actually the guy, I've forgotten his name now, but the EDG employee basically went to the committee and begged them to remove export because it had made such a mess of their code base having to support this that they just wanted rid of it. So in the end, that's what happened. Exports, the keyword was retained, but it now doesn't do anything. So C++ 11 got rid of exports.
It's coming back, isn't it?
The keyword is getting a new meaning. So it was retained as a reserved word, so you can't declare a variable named export or anything like that. And for C++ 20, yes, we're getting modules, and export will be used to say that I want to export a definition or a name from this module. So yeah, it's coming back, but hopefully in a more usable form than export was. So we declare a template like so. We introduce it with the template keyword. We put our template parameters in angle brackets. And, here, how were you concentrating last week? How many different kinds of template parameters are there? 3 different kinds. What are they? Michael's itching to answer. Go on.
I don't know. I would have said 2.
You would have said 2?
Yeah, but I don't know. I know the type parameter.
Type template parameters, yes.
Non-type.
Non-type template parameters.
And another one, template parameters.
Template parameters, yes. Template parameters, which, as far as I know, the main use for template parameters is for people to show off how clever they are. They're weird and funny to use, and yes, I've done a little bit with template parameters, but they're weird and they make my head hurt, and yes. So by and large, the vast majority of the time when you're working with templates, you'll be dealing with type template parameters. That's what we have here for this function template declaration here. So we've got template angle brackets type name T. So this is saying T is a placeholder for some type. we're going to be given when we instantiate this template. We can also have non-type template parameters, and that's where, rather than type name, it's rather confusing terminology, I know. Instead of the word type name there, we use an actual concrete type. Now there are severe restrictions on what you can use. It's going to change, it's going to be broadened a bit in C++, or quite a lot in C++20, but in current C++, you can use integer types, enumerations, which are sort of integers in disguise. You can use pointers, pointer types, including function pointers, and references, but yeah, very few types that you can actually use as a non-type template parameter. The most useful one you'll see most often is integers. So one class you're probably familiar with, or one class template you're probably familiar with that uses a non-type template parameter is standard array. Standard array has a type template parameter that says what kind of type that this array holds, and then it has a size t template parameter, which is a compile time constant that is the size of the array, the number of elements in the array. The other thing to say, and I can't remember if it says it on a bullet point lower down, but the other thing to say is that where we've got the type name keyword here, mostly for historical reasons, we could alternatively use the word class. We can say template, angle brackets, class T. And those two meanings are absolutely identical. They do exactly the same thing. They both introduce the type template parameter. The reason for there being two is largely historical. The type name keyword was introduced later. You can write type name, angle brackets, class T. It's perhaps slightly misleading because you're allowed to instantiate that with non-class types. So int is not a class type, but you can instantiate a template argument with an int. So for that reason, I'd recommend writing type name. I always write type name, but still some people use class, mostly because it's 3 less characters to type, I think. So here we have a function template declaration, and we have a class template, both of which take one template parameter, one type template parameter.
You wouldn't use class for class and type name for function.
Would you use class in a class template and type name? I mean, you could. They mean exactly the same thing.
It's not a big thing.
But no. I value consistency, and I think template type name T says it better. So within the body of our template, so we haven't included a body for my function there, but we assume it appears somewhere lower down. Within the body of that, the name T can be used as a placeholder for a type. So we can declare a member function of my class, for example, that takes a parameter of type T. And when the compiler instantiates my class, produces a specialisation of my class, say for int, then it will substitute. It's actually called type substitution. It will replace T, the placeholder, with the actual concrete type that we've instantiated it with. So there we go. That's almost all of last week's revision, with a little diversion talking about export as well. So you're getting bonus material, haven't even paid for. Before we go, any sort of lingering questions about this sort of very basic introductory stuff?
Specialisation.
Sorry?
Specialisation.
Specialisations. Yes, we'll be talking about those right now. Yep, so we have our, let's say, class template, and it's a blueprint for how we build a class. It has template parameters, And when we come to actually instantiate this class, we tell it the real types we want to substitute in. The compiler takes our blueprint and it produces a real class that we can use. But sometimes we want to sort of special case particular types, or sometimes particular values. You can have a specialization for non-type template parameters as well. But let's concentrate on type template parameters for now, just because it's easier to fix on one thing. You might want to produce a custom version for one particular type. Slightly different implementation, perhaps a more efficient implementation. Perhaps we want special behavior when our templates are instantiated with a particular type. So we might be able to, if we know we're dealing with ints, we might be able to produce a more efficient version of an algorithm. You know, might use SIMD instructions, say. For example, if we know the int and we know the size of it, and you know, we can specialize our algorithms like that. For class templates, holding an array, maybe we want a specialized representation for bools that packs them nicely, and then, you know, 20 years down the line we realize that was actually a really bad mistake, but it's too late to get rid of it, which is exactly the case with standard vector. But the C++ template machinery gives us the facility to produce what are called explicit specializations. So normally what happens is that we provide template arguments, we instantiate a template, we provide the template arguments, the compiler goes ahead and performs the type substitution and produces a specialization of that template. That's an implicit specialization, one generated by the compiler from a template. We can also provide explicit specializations, effectively overriding what the compiler would generate, saying to the compiler, well, no, don't generate anything because I'm explicitly going to tell you what this specialization should look like.
Just a quick question. It keeps confusing me, but SIMD, is it like, do I have to think about it equivalently to concurrency?
No, so SIMD, single instruction, multiple data. So it's basically like SSE instructions in your special processor instructions.
Which processor arrange data? One's like vectorization.
Vectorization, exactly. That's exactly what it is. So yeah. So modern CPUs have a lot of these extra instructions: AVX, SSE, AVX2, blah blah blah. Lots of them.
Pipelining. Is it just like a overarching?
Well, pipelining. I'm not an expert on these things. Pipelining would be a slightly different thing, but yeah, sometimes the compiler can automatically vectorize if it knows the target machine and stuff, and it can see that you're working on. You know, it can use specific instructions to tell the compiler that you can operate on 4 ints at the same time, let's say. But sometimes, particularly, you know, if you're doing really high performance work, you might want to explicitly use the sort of compiler intrinsics to do this manually, to really try and generate the most optimal possible code. So, yeah.
Is there a term like non-explicit specializations?
Yeah, so explicit specializations are the one you, the programmer, provide. And we don't really use the term, but an implicit specialization would be one that is generated by the compiler from the actual template blueprint. Yeah. So let's have a look at what one of these explicit specializations would look like.
So usually when someone talks about specializations, they mean explicit specializations.
Yes, yes. And again, there's, well, actually I'll talk about that in a moment. Let's just, we'll have a Just a little look. First of all, we've got a class template. Class template is called wrapper. It takes a type of template parameter. We've got a constructor, which copies in the value. And then we've got two accessor functions. We've got get value and we've got set value. So hopefully, you guys have all been doing this for ages. You can see what's going on with this. So now we want to tell the compiler that we want to create a specific an explicit specialization for integers. And the way we do that is, first of all, we use the word template and we give it an empty pair of angle brackets. This is what we call a full specialization. And we say struct wrapper. We don't actually have to use the same class key. We could use struct and class and struct. That would be okay. We say struct wrapper, and then in angle brackets we put int, the type we're specializing for. And in fact, if wrapper took multiple template parameters, then we would write multiple template parameters in there. Because we're specializing all of the template parameters with concrete types. So in this case, well, our wrapper is just going to have one member, which I call value. So now,
So do you have to have the same number of arguments in the wrappers?
have this.
So if you had template T value, comma T value 1 in the original one, then you need int, comma int in the second.
So if you had like type name T, comma type name U
Yeah.
in the primary template, and then down here,
Would you need int, comma int?
yes, if you were doing an explicit specialization, yes. It doesn't necessarily have to be the same. You could do int and float, and you could have a specialization for float and double. And,
You need to.
but to do a full specialization, yes, you need to provide two. So here we're instantiating our wrapper with the type float. So what's going to happen is the compiler is going to look up here. It's going to go, okay, so wrapper is a template. Before I do anything, do I have any explicit specializations that match T equal to float? And it's going to look and it's going to go, well, the only specialization I've seen is for ints, so I'm going to go ahead and I'm going to generate a specialization myself using the primary template. So now we'll create another wrapper. This time we are using an int. So it's going to go, so okay, wrapper is a template. Have I got any specializations that match T is equal to int? And yes, it has. It's got this guy down here, so it's not going to bother generating its own specialization. It's going to use the one we've given it. And then wrapper and int down here. This is just effectively just a regular class. We can just do wi.value equals 8. Sorry. And I asked this last week, but I'll ask it. What if we do this? What if we do wi.getValue? Michael? It won't compile. No, it won't, because wi is of type wrapper of ints. We look at wrapper of int here, and it's got no member function called getValue. So it's going to be a compile error.
I think I've seen this on oddity recently. If you take the first line of float and you give it no template parameter, so you let it infer, but else leave the line the same, it would default to int, wouldn't it? The construct.
No. So what you're talking about? Well, hang on. Just let me finish the point about it. So what I was trying to demonstrate with this last line, really, and it's quite an important thing, is that the compiler doesn't enforce, well, pretty much anything at all about specializations. You can have different members, different member functions, different member types. Effectively, it has no relationship whatsoever with the primary templates, which is quite an important sort of thing to bear in mind. But your question was, in this line, const wrapper angle brackets float, what if I got rid of this angle brackets float and just wrote const wrapper WF 3.14? What happens? Well, that's actually a C++ 17 feature. It's called class template argument deduction. So, basically forever, C++ has had template argument deduction for function templates. I'm going to talk about that in a minute. New for C++ 17, we have this facility to deduce the template arguments for class templates. And how this works is a bit not entirely obvious at first, let's say. But basically, it uses, it looks at the constructors and it generates what are called deduction guides from those constructors. And you can also provide explicit deduction guides as well. This is something I might actually go into a bit more detail about in a future session, depending on how many of these sessions we manage to have on templates. But effectively what it would do is it would look for a matching. It would say, okay, well, if I just considered this as a function template, what type would T have? And in this case, actually 3.14 is a double, so it would deduce T as being a double. But importantly, that only considers the primary template. It doesn't consider specializations at all. So actually, if you got rid of this angle brackets float here, it would actually deduce a wrapper of double in this particular example.
When you say it doesn't consider primary templates?
No, it only considers the primary template.
Does that also count if a specialization for that type exists?
Yes. Yes. So
if you have double specialization was double, then the compiler will use this specialization.
No, I've perhaps said something slightly misleading. It will only produce implicit deduction guides from the constructors of the primary template. However, once it has selected the template argument, then it will go ahead and use the appropriate specialization.
So if you had wrapper nothing but the WI4,
yeah,
it would still go. Would it go to primary?
Okay, so what would happen in that case is that it would look at the constructors of the primary template. That's this guy up here, const tref value, and it would say, okay, if I consider that as a function template, what type would T deduce to? And it would deduce to an int. So then it would say, okay, now I'm going to go ahead and I'm going to create wrapper angle brackets int. Oh look, I've got a specialization of that. Okay. And luckily, it just so happens that like WI curly braces 4, that would actually be a valid instantiation of the specialization, but it wouldn't have to be. So actually, this can result in some funny and unexpected behavior. This class template argument deduction. This is going to be great for a feature lesson.
Okay.
If the value in wrapper int would be private, this would work.
Correct. Yes. This would only work in this case because wrapper is an aggregate. Yes.
So you are not guaranteed if you will not use int angle brackets and say like wrapper WI4. So you are not guaranteed that the compiler will use explicit specialization. Right?
In this case, it will. Yes, because if we just had this, it would deduce T to be int, and then it would instantiate wrapper. Or except it wouldn't. It would look and it would see I've got a specialization for ints. We're getting distracted by CTAD, which is great, but you know, that I was gonna leave that for the future. I thought that was going to be a good fun little lesson or part of a lesson. So, but since you guys are all interested in it, I will definitely do that.
It's all problems that are waiting to come.
So, what kind of templates can actually take it away before I give the answer? What kind of things in C++ are we allowed to templatize? What kinds of templates are there? I've already told you class templates and function templates. There are two more things that we can have. Variable templates. So in C++ 14 we can have variable templates. And we might, towards the end of the lesson, see an example of variable templates.
And using templates.
Using templates, alias templates, yes, absolutely. So in C++ 11, the using keyword got a new meaning, an additional meaning, as an alternative to the typedef keyword that's been in C and C++ forever. So we can use the using keyword to introduce an alias for a type, and we can actually have alias templates as well, which are very useful, really useful. But we cannot specialize alias templates. However, we can specialize class templates, function templates, and variable templates. So everything else we can produce explicit full specializations. So explicit specializations are the official terminology. That's what's used in the C++ standards. So that's what I'm endeavoring to use tonight. These things, the kind of specialization you saw on the board just then, colloquially, people generally refer to them as full specializations. And the reason for that is to contrast them with partial specializations that we'll talk about in about 2 minutes' time. So it's a weird thing, but an explicit specialization is not a template. An explicit specialization, that is where you have explicitly supplied all the template parameters, saturated in, again to use the terminology, the template parameters. That's no longer a template. That is a real class, a real function, a real thing you can use. So yes, we can specialize class templates, function templates, and variable templates. And specializing class templates and variable templates is fine and very useful and something we do reasonably frequently. Specializing function templates, on the other hand, is not a particularly good idea. The function overloading rules in C++ are really complicated, as you might have noticed in your C++ careers so far. In simple cases, they make sense and do what you expect, but it's not very hard to create an example that surprisingly calls a different function. And this gets even worse with function templates, because we can have we have overload resolution that tries to select between almost equivalently viable function templates. And then we get specialization involved in the mix as well. And it all gets really extra confusing, because the overload resolution only works on the primary template, and then we have a specialization, and then we can have which primary template the specialization pertains to depends on where it appears in your source code, which is just yeah, exactly. So yeah, and I mentioned this on the last slide as well, is that a specialization need have nothing in common whatsoever with the primary templates. You can do whatever you like in a specialization. Yeah, so a specialization of a function template could have a different return type to the primary. Yeah.
How does it know what belongs to what? I mean,
Sorry, I lied to you then. No, I can't. This is what I rarely do, function template specializations.
so you need the same. You need the signature must be the same.
Yes, but the actual implementation can do anything. But forget about specializing function templates. Don't do it. If you find that you need to, there's a neat trick you can do actually. Not a trick. An alternative to specializing function templates is to have just a regular function template that dispatches to a static member function of a class template, and then you can specialize that class template to do different things for different types, and that's usually a much better alternative to specializing function templates.
Would you suggest that for? I mean, if you're writing a library, you would probably want to make use of templates on a broader basis than in production code. So,
if you're writing a library, well, it depends what kind of library you're writing, but
let's say a header library or like a templated header library.
template header library, yes, yeah.
I mean, like most libraries,
Well, certainly a lot of them, it's a popular thing to do in C++. So yeah, a lot of, as I say, many, if not most, of the Boost libraries are these header-only template monstrosities that are incredibly clever and generate usually very efficient code, but aren't always easy to understand and easy to debug as a result. So yeah, you can do anything you like in template specializations, but as with all things in C++, just because you can doesn't mean you should. So you can do crazy, clever things. Clever, by the way, is not always a compliment when it comes to code. In general, make it as simple as you can and only complicate things when there's a pressing need. That would be my sort of life goals for a programmer. Make it as simple as possible, but no simpler. As simple as it needs to be. And I'm just going to go off on a tangent because, frankly, there's no one here to stop me. So, but it's actually an interesting thing that I have noticed in my career doing this is that the more experienced programmers are, I don't want to say the better they are, but actually yes, basically. As people get more familiar with languages and get more expertise, their code tends to look simpler. And if I look back at stuff I wrote sort of 10 years ago, or even 5 years ago in some cases, I made it much more complicated than it needs to be. And now I go back and look at it, and now I go, oh, well, why didn't I do this, or why didn't I structure it this way? I think it's particularly with C++, although I have heard about it in other languages as well. But yeah, the more expertise you have, the simpler your code often seems. So simple code is or should be a goal. It's all very well to do insanely clever things, but it's not always the best idea. So anyway, yes, talking about specializations. Just because you can do something clever doesn't mean you should. We have the power to do whatever we like in C++. We have the power to make the plus symbol format your hard drive. Don't do that, because that would be a really silly thing to do. It would confuse anybody who's trying to use your code. And it's much the same with templates. If you're writing a specialization that you are writing because you want to write a more efficient version for these particular parameters, make sure that it has the same interface, does the same things as a specialization of the primary template would. This is why the vector bool specialization is a bad thing, because it behaves differently to a vector of char, say, or a vector of int. Because it has this packed representation, it means you have this sort of weird proxy reference type thing. So vector of bool behaves differently, and that's unexpected and surprising and a bad thing. So don't surprise your users, basically. I mentioned this already, but with regard to function templates, yeah, they really interact in very strange ways with function overloading, and that it's possible to change which function template you are specializing merely by putting your specialization in a different place, or including headers in a different order.
But if you have two functions with the same name, and one is a specialization for a template and one is an overload, or one is
An overload.
specific, like specified function, fully
Yeah.
specified function, the compiler would complain. He would
No, it wouldn't. Okay, so this is to do with overload resolution, but there is a rule. It's that actually the final overload resolution tiebreaker is that if you have, say, a function like add int comma int, so that's not a function template, just a regular function, add int comma int, and you have a function template type name t, add t comma t. Right, so we've got a function just for ints, and a function template. Those are overloads. There's no specialization going. So what the compiler is going to do there is it's going to see, okay, if I substituted int for t in the function template, I'm going to end up with two signatures that are identical. Which one do I prefer? Well, it prefers the non-template. So you can overload the same name as a template and a non-template, and all other things being equal, but only if all other things are equal, will it prefer the non-template version. It's one of the overload resolution rules. So anyway, my main reason for including this slide is so that I can again tell you about this, my favourite little paragraph, my favourite sentence in the C++ standard. I don't know how they managed to get a limerick in there, but I love it. When writing a specialisation, be careful about its location, or to make it compile will be such a trial as to kindle its self-immolation. They managed to sneak that around, you know, pass through all the committees. There is actually, just ahead of that, there is a really, really dense block of text that is specially written to make the reader's eyes gloss over and just go, oh. You know, it's an incredibly dense, unreadable paragraph of text that is just above this limerick, and then they snuck in this little Easter egg. There are more Easter eggs, by the way, in the index of the C++ standard. That's the place people go to put jokes in there.
Is there a way to get the standard without paying £200?
Yes, so you can get the official standard, the officially published one from the ISO. Yeah, it costs, I think it's $200 or something. But the final draft, so the ISO publishes the standards and you have to pay for those, but draft versions are free. And the final draft is available for download from isocpp.org, and that is basically that is identical. That's the final draft. That's the text is identical except for the fact it says final draft rather than officially published standard on the front page. Otherwise it's identical, but you can get that for free. So yes, if you really want to read this 1,200 pages of standardese, but you can look on that section 17.7.3.
You sometimes have the feeling that you want to be able to communicate with some people who have already years of experience. You need to know standard.
Yeah, it's actually it's on Stack Overflow a lot. People will quote from the standard text, or demand, or if you answer something, they will demand a quote from the standard to, back up your. Because people on Stack Overflow are like that. There's also a website that is I'm not sure I should mention it on the stream because it's strictly unofficial, but it's eel.is/something that I can't remember, but Google will find it. And that's a website that it's generated from the LaTeX sources. So the C++ standard is written in LaTeX and the source code is on GitHub actually. And somebody has taken this latex source and generated HTML from it, so it has like a hyperlinked set of pages on this website, which I find a lot easier than dealing with a 1200-page PDF if I need to go and read the standard for any reason, like if I'm implementing a library or some mad thing like that. So yes, anyway. Last week I gave you a bit of time to go and complete exercise 3 of this little set of exercises on templates. So we started off with an int pair class. We started off with this int pair class, and then I wanted to turn this into a template. And then exercise 3 of the set was to, I believe, write a full specialisation for, so we turned it into a generic pair of 2 different types, T and U, and then I wanted you to do a specialisation for 2 ints. So you were all here last week. Did you complete that? Yeah?
I just finished off.
I seem to remember everyone doing it.
You mean all of it, or
Not
Exercise 3.
yeah, 3?
Yeah. So I propose, unless anybody vehemently objects, that we will move on. Yeah. All right. Let's talk about partial specialisations then. This is the bit we didn't get to last week. So, hey, I've done pretty well. Taken 55 or 49 minutes to get to the stage we were at last week. Excellent. Yeah. So, class templates, function templates, variable templates, we can have explicit specialisations, also known as full specialisations. With class templates and variable templates, we can do something else as well. We can have something called partial specialisations. And partial specialisations are used if we have, one of the uses, say, would be if we were to have multiple template parameters, is what you were pretty much asking earlier, I think. If we had multiple template parameters, we would just fix one of them. So if we had, template type name T and type name U, we might write a partial specialisation where T is equal to int. Or actually, I've done it the other way around in this example. So here we've got class template, takes 2 template parameters, T and U. And now in this case, we've got a partial specialisation. So in this case, we fixed U to be int, and T is still a template parameter. So the difference with an explicit full specialisation, we would, in that case, this would be empty because we've got no remaining template parameters, and we have a concrete type there instead of this placeholder T. So it's the same syntax, basically. If you look at it, the explicit specialisation is almost like a special case of partial specialisation, sort of, if you want to think of it like that. And one thing to note is, whereas an explicit specialisation is no longer a template, we have saturated the template parameters, it is now, a real class. A partial specialisation is still a template. As you see, we've still got this placeholder type T here. So let's have a look at some partial specialisations. And we can see that actually we can do this sort of clever pattern matching thing. Almost pattern matching. So here we've got our primary template, our general version, just a class template, 1 template parameter, type name T. And now we've got a partial specialisation for pointer types. So what's going to happen is that we instantiate our class template with an int. It's going to say, okay, do I have any explicit specialisations for an int? No, I don't. Okay, do I have any partial specializations that match kind of this pattern? Well, no, int is not of the form anything star, so this one doesn't apply, so it's going to use the primary template. It's going to generate a specialization from the primary template. If I were to instantiate or request an instantiation of class template angle brackets float star, it's going to say, okay, do I have any explicit specializations for float star? Well, no, I don't. Does it match any partial specializations I've got? And well, float star is of the form pointer to something star. So it will say, actually, this will succeed if I write float in here. This will succeed. This will match. So it will generate a specialization from this template, not from the primary template, but from this partial specialization. We can do even more clever things than that. If I were to instantiate class template of vector of double, it will look, do I have explicit specialization for vector of double? No. Okay, is vector of double of the form something star? No, it's not. Okay, so we're going to ignore this now. What about down here? So, well, actually, if I deduce T to be double, then this specialization succeeds. This substitution in here succeeds. So I'm going to generate my specialization from this template, not from the primary template. So this partial specialization is sort of, it's crazy powerful machinery that's built into this, effectively a bit like pattern matching built into the language. It's
I don't understand what T is like the vector is.
So that's the type of element, the element type of the vector. You know, we have a vector of int, or a vector of float, or a vector of double.
It's not type name T of the template above.
Yes.
It is.
Yes, it is.
Okay,
So what it tries to do is, let's say we have class template. We want to create a variable of type class template of vector of doubles.
Okay. Yes.
Okay. So that's going to succeed in the primary template, of course. It would deduce, in this case, this T would be equal to vector of double. But it's going to try out all of its partial specializations as well. It's going to say, okay, is there any T I can deduce for which T star would match standard vector of double? No, it's not, because it's not a pointer. So it's going to say, okay, is there any T I can deduce here for which standard vector of T matches standard vector of double?
Oh, okay.
And there is. And that's with T equal to double.
It's a bit like in first lines of code for a string, for a span.
Looks like the first lines of code for span.
Yeah, I mean, you would need a specialization for if you pass it to a pure C array, and another specialization if it's any of the standard library containers.
No, span. I can tell you this because
I've seen it.
I've implemented span. Span has doesn't, well, you could. All right, it would be possible to implement span using a partial specialization for when the extent is equal to dynamic extent. However, what you're talking about, actually no, span just has a bunch of overloaded constructors. It doesn't use this partial specialization.
Is your implementation like the standard library one that is coming soon?
My implementation should hopefully exactly match the committee draft, yes, it should be.
Because somebody else posted it on Stack Overflow.
Did they? Oh, excellent. There we go, fame at last. Yeah, so if there are any differences between my span and the official one, then let me know. So, is everyone clear about what's going on here? What these different sort of partial specialisations mean, and how this sort of weird, it's actually even more complicated than I've tried to explain it so far. But in this sort of single parameter case, is it sort of clear what's going on? The compiler will effectively try and say, in this case, is there any t that I can deduce such that this will match my given argument type? That being the case, if you've looked at this and gone, okay, yeah, that makes sense, you might be able to see that, although it's not in the example I've given here, but you can perhaps see that it would be possible to have multiple partial specialisations that match a particular type. This can happen. And in that case, there are a set of really complicated rules about what constitutes one specialisation, partial specialisation being more specialised than another. So we've got a set of really complicated rules for deciding which function we prefer over another, given a set of arguments. That's called overload resolution. And then we have another set of rules about which, there's a helicopter landing on the roof, I think, which partial specialisation we prefer over another. These rules are pretty complicated, but the most important one to gather is that if we have an explicit specialisation, that is a full specialisation, that's always going to be preferred over a partial specialisation. And the other thing is, if there are equally well-matched partial specialisations, you will get a compile time error. It will say, well, the error is actually literally ambiguous partial specialisation. So this is a lot less problematic than overload resolution, although it's sort of conceptually similar. Overload resolution can be problematic because it tries really, really hard to call a function on your behalf and often picks the wrong one. With template partial specialisations, it's a lot, in general, it will just say, look, I don't know which one to choose, you're going to have to tell me.
Would you ever get any more?
No, you just get a flat, it's just an error.
Okay, so even if you think you want it, you won't actually pick up the exact amount to pick one.
I have rarely had it accidentally pick the wrong one, let's put it that way.
They can't accidentally pick wrong, unless it's a bug in the file.
Or a bug in your program, yes.
It's never wrong, you are wrong, not compliant.
Yeah. But actually, well, I was thinking about doing it next week, but we'll see. But actually, we can use partial specialisations with a trick called SPHENET, substitution failure is not an error, to do some really quite clever things. But we might get into that a bit next week. That gets into some really hardcore template stuff. But for now, exercise 3 of that little set that I gave you, we were talking about explicit specialisations. I wanted you to create an explicit specialisation for the case where we had 2 ints. Now I want you to have a go at writing a partial specialisation of our pair class. I think I asked you to do it where the first parameter was an int, I can't remember exactly. But if you go to that URL and have a look for exercise 4, you guys were all here last week, so you've probably still got it there on your machine. So have a little go at that. And as always, let me know if there are any problems. Oh no, they're having no forward definitions.
Yeah.
That was the thing that's deprecated.
Weird compiler errors.
You're getting weird compiler errors.
It's the best.
Legendary.
Managed to.
So the error was that I didn't template return type, but it says returning reference to temporary, which is not true.
Which one?
Well, I corrected it now, but I forgot to template the return type, so it was still good.
Oh, so it was doing a conversion.
Also, where's the instantiation?
Yes.
Well,
Yeah,
was
so it was
compiler.
creating a temporary int.
Yes. Ah,
And then finding the reference to that temporary int, which was about to go and step. That was the error.
No, the result of indexing a stood array is.
Yeah, but he was returning an int, and the array held doubles.
It looked like this before, with the error, so there was a trouble.
Yeah, because it's performing an implicit conversion, and because of the conversion you end up with a temporary.
Ah, no,
So
it's
I would just return by value. It's marginality, that's the optimization. But
what's mechanism?
if you return by value, it doesn't matter for ints and stuff. It's like a what's the word?
I realized that if you would want to write cache
Basically, the way I write this is I would inhibit selection of these if it inhibits a conversion. So I'd have these. I would allow to return ref in case of it not being a conversion. But I basically spin it out. So you could use concepts to do it as well, but in C++ you use spin it instead. But it's not like basically you could just return.
I have a problem with the ref, because I mean for primitive types I'm starting to get it, but it just doesn't make sense. But even if you have like short breaks,
Sort of guessing a little bit.
if you avoid interaction using references,
I've got it.
Partial specialisation there in case we two didn't know. That's what I asked you to do.
Okay.
I'm using
Optimizations turn
trying
up
to put
by
in.
level.
So the first could be.
It doesn't stop the compiler from seeing
Template could be
through.
for a second.
Only if you
It's got to be
change
linear
change
change.
the So if
Partial specialisation. A case where the two template arguments refer to the same type.
Two
just put it in register because it needs to affect the original value. Although that may not matter either if it can see that afterwards you don't use it.
So it's got to be
So
taken.
generally speaking, references, simply using references doesn't work, so it's fine. Slowly, yeah.
So can I put the same thing in again?
Is that interesting? Is that yours?
I would expect as long as the value
We have to give the.
I have to give it.
is not like,
But it's the same type, isn't it?
Yeah.
as long as it's
And
close
then,
enough.
and then I should be able to put, should P, then, because I've defined P as an array of types here, I should be able to do the same as we did before.
For the experiments that I've done, usually type may not optimize
Okay.
references.
So, yeah.
Give me an example.
And then on the return.
And there might be a reason you can't.
I think
Yeah,
it was
it's
very
the
easy.
array,
It's
so
a
the return type
volatile, return type is really
is going to be T, isn't it?
Oh yeah,
So
you
you
want
can't
to
see
be volatile, that will change everything. Then you change everything. That will do the same to the pretty much any optimization anyway. Once you mark something volatile,
I can't remember now which is this.
That's correct.
but you generally don't use
What's
it.
the difference?
The only time you should use
Between
volatile
the-
is a pointer to
Well, it won't go
some
on
memory address that's
That's
in
the
fact a hard
Constant on
device.
either side of
That's
it.
when you're doing stuff and changing it, you can't predict it. Otherwise, anything that's not volatile, especially if you do that optimization, might into the whole program. Regardless of this reference point.
I have read with some
test it, yeah, yes.
Well, did you? Because you've still got your in specialisation as well.
Yes.
Yeah, it's a second.
You're not used. Oh, you're there, double time.
Yeah.
Only case where that would be possible is if you tell the compiler to mince an executable library
We do care charge.
and you give it a list of multiples,
So
because then it knows
if you want to
based on the
get
arguments
really
given
fancy,
that
you could put a message in the constructor to say which specialisations
and
may
it
use
needs to
just to
Just to see out.
and then just knows that
make sure
everything you
everything's
give it must be exactly something you need to spit out an executable, and therefore it
So,
would effectively work just like on optimization. If you've got source file A, B, C, D, and all of those are going to be spat out as a clear program. If, however, you're telling it to have object files, there is no way for it to know or do that. You have to tell it explicitly, I'm going to do things optimization, and I will call it back at the next stage. Otherwise, it's just no it's no. He's talking about implicit RTL, which can kind of
not unless you like use object files. Yep. But that's not a double tap, that's just same.
Anyway.
Same
same
template.
thing, yes. Yeah, I was just wanting it to come out from the top.
I have stuff that I can talk about.
Oh, this is-
Ah, so
That's
you have a
not-
specialisation
I'm
to
trying to remember
the
the
exercise at the top.
Windows introduces its own types.
Maybe we can do the right specialisation.
Maybe it's
Yeah,
surprising.
two bits.
Static has.
Yes, it's the top one. Top one.
give me an example. So when those are very C, that does happen, but
So, for example, something even if
that's a static assert, that's not a static cast. Okay, static cast, here we go. Token. So what is token?
this makes sense because token is size to
Yeah.
and I'm casting to the
Right, so why don't you take
And then expecting.
Yeah,
Because I'm defining an instruction. Yeah, so yeah, it makes it and then it prints it out.
pointer to a unit?
well, it's just it's a technical example. It's not a contradiction.
Oh, this is.
Yeah, I think the
Why don't you
key
just
here
use,
is
got it
in one
like
way. You have to think that
why don't one doesn't code
that's
this
the way I
one?
think it is they're totally separate.
Why don't you, I mean, like, why don't you just
What you wanna do with it?
outside logic, aren't you?
Is
For token. For the token.
the pilot's making they're separate entities.
No,
aren't
but
they?
instead of using size
That's
T.
the core of that. You're actually thinking I'm making separate functions.
Yeah, well, completely separate
So
classes.
I'm just putting them together.
Yeah.
The number of tokens
Completely.
by numeric such that
No, it's
No, you don't.
people that use.
Okay, so
size T is no
Yeah.
concrete
It's
outside
not.
long. Size of size T on one
so-
platform could be different to another, just as on sign on.
That's what I have here. So as long as I'm only compiling something that's usually
If you want to, yeah, but I'm saying, why would you just use that? If you're going to use size T, which is not a constant value.
Okay, so what happened is what a specialisation. Okay, so this was my example. Yeah.
If you want the same size, then you could use something like Unix 64T.
for this function calls anyway. I mean, if you want us to define this
This thing's possible.
consent long.
So,
In the beginning, I was just
Now
writing
we have
the original types because it made the code
specialisation.
But then I thought, maybe you don't
Great.
define
No,
it.
it's specialisation.
Yeah, so when it's static cast, it's unsigned, size T is unsigned, right? Why do you need to cast it?
Okay.
Stood size
So
T,
should we have a go at
stood size T on the right?
writing a partial specialisation?
It's unsigned, right? It's unsigned.
If you look at the README, wherever that was,
But it doesn't matter, it's not the same size.
anyway, down in exercise 4 down here. So you write a partial specialisation in case where the two template arguments refer to the same type.
So, but to be honest, I'm providing the token and the function should actually must change the token. So just as correct now.
Templates.
Then you just
say
the
now,
sign bit.
okay,
So rather than
so we've got a specialisation
if I have a value that's like
when the two templates, usually it's T value. Now we're saying if they're the same, we're going to use this specialisation instead. So this is this pattern matching thing I was talking about.
that takes a sign value.
Matching the pattern where T and T
Doesn't really
refer
treat
to
it
the
as a
same
sign
type.
value because it's just
Okay. So now what we want to do is we basically want to recreate
one sign to sign.
exactly what we had back here.
It will preserve the sign bit as 0 because it knows it's
So we're going to
positive.
first
It
of
will
all
just do
write
the
the structure.
However, if I reinterpret cast one sign to sign, it will obviously do nothing. You end up with it being treated as considered sign, but the top bit is just left as left alone. Right? So why don't you physically transform the bits together? Which usually is what we want. So when you use static
Actually, before we think about that,
when you're going from
Well,
an
actually,
to
just store
unsigned to unsigned. So when you're dealing with single functions, when they take sign or unsigned, assuming that you have the correct value already, probably don't.
yeah, so we've got two items and they're both type T. So this is
very much together.
So use the correct type.
Don't try and massage.
So
I'm just
I'm
trying to
explain
match
that.
function.
Should.
Use unsigned.
Yeah, there we are. So
Language.
we can see that now it's saying class pair or double has no member that you get first. Because what it's done is it's recognised this specialisation for the case where you're doing double. It's saying,
Well, I
okay,
think
use this
I mean, you could
but actually it doesn't matter.
in that case, the solution is function overload function. Have one overload function for 32-bit, have that one for 64-bit, and you can either enable one with a macro, or if you want to get fancy and do a C++ style, use a template to enable the same. So while
Just
one
more
selects the correct overload platform,
just
that's how it
construct this. This is using
one function
initializing this, initializing
one
one.
function.
Two things.
They take side to side.
It's probably the same
Notice
as
version, notice around.
It's exactly basically
Yeah, enable
exactly
the
the same
same.
as this. In fact.
Based on it.
Why do you have, like you have 64 units, 32 bits? I will learn anyway.
Yeah, of course.
Yes, but the problem is if I'm using types if they rely on being the same. Because I mean this is not a very expressive example, but for example I have another example where I have a C struct and I take
It's nearly correct.
I have a C struct overlap entry and I have it redefined as a condition status, which is exactly the struct parameter. But this function can only succeed if overlap entry
Because
exactly.
T, exactly.
So otherwise it's just going to write whatever it is.
So what? So completion status is your type, right? Which is not.
It's basically just
And you're doing that because you
Partial
didn't
because
replace it.
No, I'm doing that because
The template is saturated our template programs. We still have template
library
parameters.
is like model.
So it's not a full specialisation.
Because like the
Full
size of
specialisation where we explicitly
Your type
enable the particular
might be
type.
32 bits on one platform.
That's
It's always
a
on
full
that.
specialisation.
Check is good. Rather than using static assert, you can encode
This
it
one, because we could
as
equally
part of the template, so you can template function, that becomes part of the template.
we do like
And then
this.
if the size doesn't match, sorry, well, rephrase that. If the size does match, then
Now,
that instantiation
to be clear, this is like partial specialisation, just when the second
that's
parameter is in.
that instantiation is allowed.
This is how partial specialisation was invented, and then you've got to extend
Fails.
this to be
Okay,
this.
one moves on, checks for another one where you obviously have another template overload.
So that's how the name
Partial
partial
specialisation.
specialisation.
Then just always a 32-bit instead. And then that one's about to come into mind. So you can handle this, it's just it should be overload.
Yeah.
With the macro,
You can also just do hash if def.
Look at a different thing.
This function.
It's not very secret.
is it?
It's not very.
I've
It's just
been looking at my OpenGL stuff, you see, that's the.
Yeah, there's nothing wrong. There's honestly nothing.
Yes, so this you're explicitly stating what both of these types are.
It's not. It's
And the other one you're saying, well, I don't know what they are, but if they are the same,
so you're trusting that those macros are correct. Whereas obviously if you do it at the compiler level template, it's more intrinsic to the system because you're having the compiler actually examine the size of the time, get meaningful errors. lazy and pay for it. And you end up with the same program, with the same level of optimization. You have to pay for it at runtime.
I mean, I said, if I really figure out.
No, this is not any kind of specialisation. This is the hardware template.
It's still a compile time check.
I actually find so.
That's still a
C-line
compile
does this
time
thing
check.
like abbreviating
But it will just fail to compile.
this line.
There's no, you just
Where's the way
just
I
dead.
turn it off in the settings?
What would it
That
actually
should say
mean?
template.
Because
Should say
the
that.
way it's in regular classes.
So yeah, C-line abbreviates.
So, can I static classes?
It's a list.
Calls an array of one to one.
A static class an array of the raw class to its version.
No. Cool. That's not undefined behavior. No, sorry, new friend, it's not undefined behavior. That's just not possible.
I have conversion of that. I have conversion.
So you have a conversion operator. Well, yes, but I'm assuming all this does just returns that, right?
Yeah.
Yeah.
Okay, I think we had 100% success rate on that exercise, so that's excellent. This is nice when we got a small class. We have we have 33 minutes to go. At this point, you have a choice. I can either go on to talk about the things I was going to talk about next, which are explicit instantiation and external template, and about template argument deduction, or we can say, okay, we'll do that next week, and we'll go into the fun meta-programming crazy stuff. Not really crazy, but a bit more. John's favourite. What would you like to know the actual useful stuff?
Yeah.
You want to know the useful stuff. Okay. Michael's not paying attention.
It's a tie break again.
Yeah. Do we want the useful stuff, or do we want the kind of, that's crazy, why would you do that kind of stuff? Let's go with the useful stuff, shall we? Sorry, John. Next week. Next week.
I know it's useful, but
Oh.
it's just that the application.
Implicit conversion is not always new. Okay, there are very good benefits. This is exactly the kind of shit I do at work, where we have C APIs and we need to wrap them in a nice way. Sometimes we have to call C APIs with our wrappers.
Okay. Explicit instantiation of templates. So normally a template is instantiated when it's first used. So first time we say I want a vector of ints, the compiler will go away and it will generate that class for us. But we can actually do a fun thing, which is to explicitly instantiate the template. So here we have a function template called myFunction. And now we can say to the compiler, I want you to generate a specialization for t equals int for me, please. The way we do that is we say template void, or template, and then the signature with the type substituted. So this tells the compiler, please go and generate a specialization with t equal to int. Well, it's helpful when we get to the extern template thing, we'll see in a second. So yes, you can do this with class templates as well, but in this case we've used the function template. So this is saying, okay, here's the blueprint, and now I want you to actually construct something from this blueprint. Rather than just doing it the first time I call my function, just ahead of time, please create the version for ints. This syntax looks a little bit similar, looks a little bit familiar. This is almost identical to the syntax for explicit specializations. This first one is an explicit instantiation of this template. And this second one is an explicit specialisation, or a declaration of an explicit specialisation. And the only difference is this little empty angle brackets here. Yes.
There's an error with the first template.
You think I need int in there, do you?
No, it's not the int. It says template without any angle bracket.
That's because it's an explicit instantiation, not a specialisation. Pretty sure I got this. No, to stick into Godbolt. If I'm wrong, then tell me, please.
It only works as long as it's a declaration. It's a definition first.
Of course, because what you're saying is, I want the compiler to please go and generate an instantiation of the primary template for me, please. Please go and generate a version of this function for ints. So it makes no sense to put a declaration in there, to put a definition in there. It's an explicit instantiation of this function template. Whereas this is a specialisation. So this one actually needs to have a definition. So it's really awkward because these two look almost identical. The only difference is these missing angle brackets. Yeah.
But that means that in the first case where I don't use angular brackets, the compiler will definitely create the function for me, and
Yes.
then needs to dispose of it if it doesn't use it actually. Again.
It will be a weak symbol, so it will be merged with any other equivalent definitions in other translation units. But actually, this symbol, if you explicitly instantiate it, this symbol will appear in your binary, which can be a good thing, like for libraries, for example.
The one he's pointing to is concrete, right?
Yeah.
It's as if it wasn't templated almost in terms of the symbol.
Yeah, this is effectively the same as declaring that function. It's declaring a function called my function that takes an int and returns nothing. Except we're saying, I want you to, so create this function and create the definition from this template, from this blueprint here.
But if you didn't have template on the front,
Yeah.
it would still replace.
No.
It would still replace the template above.
Okay, but so in this line, if I didn't have the template keyword, can anybody tell me what would happen? Yeah.
Would be counted as an overload. And
Yeah, then I would be declaring a new function called my function that would be an overload of the template. So you see how this begins to get a bit messy when we've got function template specialisations, explicit instantiations, and overloading. It all gets really messy with function templates.
It depends if you want to participate in the templates or not.
So, an explicit instantiation is not a template. What we are saying is, I want you to go and generate this function, and I want you to do it using the blueprint I've given you, using this primary template here. Now, why would you do this? Well, it could be useful, for example, let's say you're writing a library, it's not a template library, it's just a regular old header and implementation file type library. Well, you could have an implementation file that behind the scenes implements something using a template, but then only offers clients versions for particular types. So rather than having my massive function in a header file and having your clients generate the specializations every time you compile, what you can do is you can put your my massive function template in a CPP file and then explicitly generate instantiations, let's say for int and float and double, if those are going to be the most commonly used types. And then in your header file, you just put a declaration of my function int, my function float, my function double. So that would be one of the rare cases where your template code would go in an implementation file. rather than a header. But it also ties in with this second piece of functionality, a new feature that arrived in C++ 11, this extern template. And I can't remember, somebody was asking me about this last week. But what happens when we instantiate the same template in multiple source files, multiple translation units, as in the terminology? Well, the compiler goes ahead and it goes and creates a function or a class from those blueprints in each and every translation unit separately. So in our first CPP file, we're using standard vector of int. In our second CPP file, we're using standard vector of int. Third, fourth, fifth, we're all using standard vector of int. And every time, because we compile things separately in C++, usually every time, the compiler is going to go ahead and it's going to generate this specialization, it's going to generate the member functions it needs. And then later on, the linker comes along and it sees, okay, all these translation units have all these identical functions in them. So I'm actually just going to pick one of them and use that and delete the others. And that's the usual way of doing things. That's the usual way that templates work.
So it's nothing wrong to do it. I mean, if it's convenient for you to instantiate the same.
Yeah, there's nothing wrong with doing it. You'll get the same final executable. The difference, well, the problem is with compile times, basically, because you're repeating the same work over and over again. It's work for the compiler to generate a specialization. Particularly if your function template calls other function templates, sort of recursively. It has to go through and instantiate and do the type substitution and do all the checking it needs to do each and every time. That's a lot of work, and that's, as I say, one of the reasons all these template libraries are really slow to compile. And then at the end, when we're merging all of our 100 translation units together, it's going to throw away 99 of these things that it's done, and it's a lot of wasted work. Well, wasted work. So work is being duplicated each time we compile a file. We're compiling the same functions over and over again, and then throwing away all but one of them. Seems really wasteful. And so in C++ 11, they effectively glued together two existing keywords. So extern and template were existing keywords. But they said that, okay, we're going to give a special meaning to extern templates. And that's saying to the compiler, effectively, just trust me that some other translation unit is going to provide a definition of this. Just go ahead and behave as if this specialization had been generated. Yeah.
But that means it could not inline unless you use link time optimization.
That is exactly the case. So if that didn't come out, it means it can't inline unless you're doing LTO, link time optimization. That is exactly correct. So the plus side, the advantage of using extern template is that you dramatically reduce your compile times. The downside is that, yes, as you say, you don't get the inlining, and that's one of the major benefits of templates, is because all the information is right there in the header files, and the compiler can inline everything and get rid of intermediate function calls and glue things together and constant folding and all the other magic that it does to make templates fast.
Do you want to point out the main motivation for using templates is being generic, really? I mean, yes, the optimizations are also nice, but they're not as ubiquitous as they used to be. Compilers are smart enough now that they don't have to use templates to get their
properly in your LTO world, but not everybody does.
Okay, if it's not an external template, fair enough.
Yeah.
But in this case, obviously, you throw that all away. You're saying that the key knowledge generic line, right? If you're going to do this, it's generic line.
Well, in this case, you name an explicit specialisation, you are saying. So what it will do in this case, it will generate basically just enough of this class that it needs to, basically enough to know its size. And all of the member functions it will assume have been generated elsewhere by an explicit instantiation usually. So if you're going to use this pattern, what you would usually do is have one translation unit that explicitly instantiates all the versions that you need, and then every other translation unit has, you probably put them in a header file, just extern template, blah, 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 blah.
Which is the generic code. I've written the class once. I wrote 5 lines for 5 instantiations. Oh, 500 lines.
So I have to say, in my experience, extern template is not all that heavily used. I haven't seen it very much. Maybe Ollie begs to differ. But
No, it's not used that much. There's the only real use case I find for it is when you know exactly what types you want to instantiate, so you can still write the code once, but you know exactly what the use cases are, and so you pick an external. And it happens to be expensive to just let it be. Or it can be a form of hiding as well, right? I have a template, I only want to let you use these kind of instantiations. It's not about performance, it's just because you should only use it with type A, B, C.
So yeah, extern template is a way of reducing this, the compile time cost associated with templates.
Do you have to be careful of which ones you label external template and ones you use for the
Explicit instantiations.
Yeah.
In a sense, they're opposites. Explicit instantiation is saying, generate a definition for me now. Extern template is effectively saying, somebody else has generated, and some other translation unit has generated an explicit specialisations, so don't do it. So in a sense, they're opposites. That's why I put them together on the slides. They're doing opposite things. So that was a little aside, literally 2 slides on explicitly instantiating templates and then explicitly not instantiating templates, declaring it to be external. So controlling template instantiations. I mention them just because it's quite useful to know that you can do these things. Yeah, by and large, they're not really all that heavily used, either of them, if I'm going to be completely honest. But it can be used to save you compile time if you know specifically what types, only what types you want to use with your templates. So let's go on to look slightly more deeply at template argument deduction. So this is the process by which, when we call a function template, by which the compiler works out from our function arguments what the corresponding template arguments should be. So, first thing to say is we can, when we invoke a function template, we can just supply the template arguments. Right, we can just say function blah, angle brackets, int, comma, float, in angle brackets, and then in round brackets we supply the function parameters. Right, we can explicitly supply the function parameters that we want. Sorry, the template parameters that we want, template arguments. For function templates, we can actually supply fewer. So if the function template takes 3 template parameters and we give it 1, the compiler will attempt to deduce the remaining arguments. Right. Ooh, my formatting's gone a bit funky there, never mind. So here we've got function template takes 2 template parameters and 2 function parameters, 2. So T and U. And we can call it like this. For example, if we wanted to, we could say my function angle brackets float, and then supply 1 and 2 as function arguments. And what's going to happen in this case is the compiler is going to say, okay, well, my function takes 2 parameters. The first one has been explicitly provided for me. So T is going to be equal to float, right? That's fixed. And it's going to say, okay, I've got 1 remaining template parameter that I need to work out what it is. Well, if I look at my function parameter, U, I've been given an int, 2 is an int. So if I can deduce that my template parameter U is going to be an int in this case. So I could have said my function float, and that would have fixed both of them. In this case, I've said the first one is float, and the second one I want it to be deduced. I want it to allow the compiler to deduce what it is from the function argument I've supplied.
So, for example, if you did the 1, 2.0, they double the float and a double it.
Exactly that, yes.
Also, you can remove float in general, and then the compiler will use both parameters.
Yes, so if I just said my function and I didn't have anything in there, that would be the usual case, and the compiler would deduce both of them. What you can't do, however, is to say, okay, I want you to deduce what T is, and I'm going to explicitly supply U. You can't do that. That's not possible. Because we have to start from the left. It's a bit like, well, it's exactly like, in fact, function arguments. You know, we can have default function arguments, but we can only start defaulting things from the right-hand side, if you see what I mean. So it works a lot like that. So we cannot, we can't say, please deduce T, and I'm going to fix you. That's not possible.
You can't use word auto.
No. Maybe that's a proposal you need to make. No, don't do that. People will hate you. We can get into a situation. Don't be fancy on this slide, right? Because words have only appeared in the top left. We can get to a situation where we can have conflicting deduction. So this is almost exactly the function template max from the standard library, standard max. The real one takes a const ref, and here I've done it by value, but it doesn't really matter. So this takes 2 parameters, both of the same type, 2 function parameters, both of the same type, which is the template parameter T. So now I'm saying I want to find the maximum of 1 and 2.0 f. That is, I want to find the maximum of an int and a float. And I haven't supplied a template parameter. I want it to deduce what T is. Well, now the compiler's got a bit of a problem. Because it looks at this first one and says, okay, going off my first argument, literally called first, okay, from there I can deduce T is int. That deduction works, no problem. Then it looks at the second parameter and says, okay, from here I can deduce that T is float. And now it's got a problem, because which one should it prefer? Should it prefer int, or should it prefer float? And unfortunately, for reasons of sanity, what will happen in this case is you will get a compile error. It will say something along the lines of conflict in argument deduction. Because each of these on their own would be fine, but we've got a conflict, a deduction failure. Whether to choose int or whether to choose float. And actually the reason I picked max is because this quite often happens with the min and max templates in the standard library. So the way to solve it is to explicitly state the type we want. So in this case we want max, where t is equal to float. So then the compiler's going to do the substitution. It's going to create a function max, 2 arguments, float and a float, also returning a float. And now it's going to say, okay, now can I convert these arguments to floats? Well, it can obviously convert from a float to a float, it's the same type, and it can convert from an int to a float as well. So that's going to work without any problem.
Wouldn't it be good practice to just put float, comma float? Is it just extra typing? It's just
What would happen if I put max or float, comma float? Yeah.
It wouldn't find any template.
Yeah, it would complain because it's your template arguments that go in there,
only we got T.
and you only get this function template only has one template argument.
Never mind, you've written it, it's all good. I was going to say, if you explicitly instantiated it, you've literally done that, it's fine. I didn't see it.
So, argument deduction can only happen in the case where the template parameter actually appears in the function's argument list. Which sort of makes sense. How do you do if you've got, otherwise it's got no information to deduce from. So here we've got function do something. It takes 2 template parameters, and it takes 1 actual function argument, t. And here, fine, it can deduce t as int, but it's got no information from which it can try and deduce u.
Would you get the error when you call do something? Would you get the error when it's trying to do something?
Sorry, say that louder.
Would you get the error when it's trying to do something with 3? Or would you get the error when it's trying to compile or do something with 5?
Which do you think will happen? So the question, if it didn't come out, would you get an error at the point of use in this, as in do something brackets 3, or would you get the error at the point at which you define the template?
I could get this wrong. I think if the void do something TR.
You think it happens at the point of use? Sorry, at the point of declaration.
Because you've got no U.
Great question. You get both.
Ollie says get both.
The compiler error you're going to get is going to say it failed to instantiate at the bottom line, and it found this particular instantiation, which obviously is only 1, but it's going to...
Your error message will certainly mention this. However, if this line didn't exist, if the actual call to do something didn't exist, there would be no error. Because don't forget, what I could do, if I said do something, angle brackets, int float, if I explicitly supply t and u, that would be fine. So there's nothing wrong with this template as it stands, because it is callable. It would be wrong for the compiler to generate an error just based on the template definition. The problem is, at the point of use, it doesn't have enough information to deduce either, but I could still explicitly specify u. Yeah, I can.
Information to compile.
I can still explicitly specify u. So here I've got the function template taking a reference, const tref, and a function taking a pointer, t star. And this is actually kind of magic. Because what happens is that I pass I to this function taking a ref, and the compiler can look at this, can look at the const t and argument, and see that it's been passed an int. And from this, it can deduce that t must be int. This is actually kind of magic and quite complicated how it works. Don't look at it too closely because it actually does exactly what you want it to. It's magic behind the scenes, but it does pretty much exactly what you want it to. You want t to be deduced as int in this case, right? So this is great. This is how we want things to work. And this deduction actually is even more clever that it works with pointers. So if I've got a float f, if I pass the address of f, it's going to say, okay, well, you've given me a float star, and if I were to use float, t as float, then that would satisfy this argument. So it's going to deduce, in the second case, t as float. Yeah.
If you would make a specialization for the first template without the constant.
So you mean a specialisation or an overload?
An overload.
An overload, yeah.
But you use the same function call for the int. It would take the one without the constant, wouldn't it?
Yeah, so if you had a second overload that was func taking ref brackets t and, so no const, then both function templates would be considered by overload resolution, and the second one would be preferred because I in this case is non-const.
But if you pass 0 directly into the function, it would choose const one.
But if
you would pass without using an intermediary variable integer directly into the function.
If I said func taking ref brackets 3, then it's going to prefer the const ref overload because an integer literal is an R value, and R value can't bind to a mutable reference, can only bind to a const reference. So we're getting a little far away from templates, but yes. Again, it does. This is the frustrating thing because 95% of the time, C++ does exactly what you want it to. And it's the 5% of the time that causes problems, that you have to bear in mind all these special cases. But for things like this is actually one of the times when C++ does exactly what you want. My screen has just died here, never mind. So here I've got a function taking a vector that I've had to split on 2 lines. In fact, taking a const standard vector ref. And miraculously, the compiler is able to look at this and say, okay, well, if I deduce t to be int, then I can call this function.
Does it look at the number of bytes assigned to each?
The number of bytes, no, nothing to do with the number of bytes, no. This is purely based on the type information. So yeah, don't ask me how this works in too much detail because, to be honest, I don't know. It's clever and crazy and mad. But 15 seconds over time. But that's a good place to stop because I was going to ask you some questions on that, and then the next thing was going to be this, which was going to be the crazy fun stuff I was going to talk about. But I guess we'll talk about that next week, assuming we have somewhere to be. So yeah. Well, anyway, we.
Next
we will see what's happening, because the week after I'm at CDP comes, so I don't think next week's the time. Anyway, right, that's it, I think, for tonight. Thank you guys for actually being the ones to be here, for braving the elements to. Thank you very, very much to Cloudflare for hosting us tonight. Very kind of them in their lovely facilities here in central London. I hope to see you next week. Thank you for anybody who's watching and or listening online. And yes, we'll possibly continue talking about templates next week. Thank you very much.